been quite 100% finished. And the only new thing I'm going to talk about today really is going to be what I call linear contrast. So recall the last time we met, we ran this simple little program. And this was on this data set called NAS1 composite. So let's look at that real quick. That's this one. And so recall that's a data set with just the number per core, the number of species per core. Not a very interesting data set. And we ran a quick ANOVA. I'm just going to run it on log and in fact, you know what? I'm not going to use log. Let's run it on count. The number of individuals per sample, which is N, and the number of species per sample, which is S. Okay, well the important thing was going to run this, what?
I don't think we have that composite data set. Do you all have?
Well, you should have created it somewhere along the line. It's there. You know, but this is not news. If we go back to that Ed 16, I'll bet one of these programs is going to create it. It's probably going to be this one. No, it's already created. But it's real simple. All you're doing is running a proc means on the NAS1 data set. And you're getting the total number per sample and the total number of species. We've actually run this. We must have done this almost every class the first 3 or 4 weeks. The important thing is this line right here. This is what we introduced in the last lecture. This is the mean statement. And we're going to use Tukey tests and lines. Now, what is Tukey again? It's a multiple comparison test. So I'm going to kill that and run this. And the important thing is the probability value is 0.13 for N, and that means there's no significant difference among the means. And if we look at this, this is for each of the 4 stations, and as I recall, the line is the mean, and the symbol is the median. And by the way, a sample like this, where the mean and the median intersect, is pretty much a perfect distribution. It's going to be a normal distribution. They usually don't intersect, but that's okay. But one of the important things when you look at this is that the variability in this station is a hell of a lot less than the variability in some of these other stations. And one wonders whether or not this individual one is completely different from those. So according to the Tukey test, and for number of species per core, it's the same thing. And according to the Tukey test, you know, even though there are only 3 individuals compared to 27, this group, this is all the same. Okay? So imagine, well, before I get into that, and the same thing here, So the bottom line is, this is not a really interesting example because there are no differences between the station means. Now, this is kind of a nice little picture, but sometimes we may want to, let's make believe that we call it the second number, 0, the 10, 100, 1,000. We call that its distance from the shoreline. And so, like, let's make believe that these are actually some kind of numbers, and we actually wanted to connect those lines because they were along a gradient or something like that. How would we build a picture like this? Well, let's say we wanted a picture with the mean and the standard deviation. That's what I wanted to show you down here. So what we can do is we can calculate the means. And I'm just doing log n here. Okay. So now we have a data set called X. And I'm going to go up to my workdeck directory. And now, for each of the three replicates, we have both a mean and a standard deviation. Whoops, is that right? Yes. So, I've got log n and s log n for standard deviation. So now the first thing we need to do is back transform these things. If we wanted to plot the if we wanted to plot the data that was actually in the analysis. So the most important thing I'm telling you right now is the only correct way to plot data is to plot the exact data you also did your ANOVA on. Now, a lot of reviewers and a lot of journals will give you a hard time about this, and they're wrong. But to present the data for just the untransformed in your plots when you did the ANOVA on the transformed one, that's just completely wrong. The reason is because the graph has nothing to do with your statistical analysis. Why would you do that? So you can show them a graph, but why show them a graph if it has nothing to do with your statistical analysis? So my point here is that there's a break in logic. And I strongly, strongly believe that if you decide the correct way to analyze your data is with a log transform or some other transform like a root transform, then don't present plots of the raw data, present plots of back transform data. Now, what is a nasty detail? So if we take a mean of the raw data, we're going to get one number. If you take the mean of the the transform data, you're going to get a different number. And that different number is always smaller. Why? Because it's math. Because the nature of a log scale is that it's big in the 1, 2, 3 range, and it's tiny in the 8, 7, 8, 9 range, right? So you've got to get a lower mean. It also means that your error bars are not going to be even. The error bar on the low end is smaller than the error bar on the big end. So how do we plot such a nasty thing? Well, the first thing we do is we've got to back transform it. So first, the mean is going to be the exponential form of the new variable log minus 1. Why is that true? Because this value is the natural logarithm plus 1. It's n plus 1. So when we back transform using the exponentiation, we have to subtract that 1 we'd added originally. So now, the lower bound is going to be the mean minus the standard deviation. But now we have to subtract 2. Why? Well, because we got 1 there and we got 1 there, right? So since we're using it twice, we got to subtract 2. What's the upper bound? Well, it's going to be the mean plus the standard deviation, again, minus 2. So now we have a mean and a lower bound and an upper bound, so this is the mean plus or minus standard deviation. How do we plot that? Well, we can use proc SG plot. So let's go ahead and run this. And we've got back. And now what we have is D-transform mean, a D-transform lower value, a D-transform upper value, okay? As opposed to just the log and the standard deviation. So if we plot just the log values plus or minus the deviation, the numbers are going to be exactly what you get here. I should have used that one. So what we can use is SG plot and the scatter option. And the way scatter and series and a lot of the plots, a lot of the statements in SG plot work is you tell it what your X variable is, you tell it what your Y variable is. And notice, in this case, X is actually not a number, it's actually a categorical variable. So one of the beautiful things about SG plot is it doesn't care if it's characters or numbers. It'll just plot it along the axis in whatever order it comes up to first. Now, so we're going to, on the Y value, we're going to plot the mean. And we want it to plot the error for the lower, which is this value, and the upper, which is this value. And by the way, if both X and Y vary, you can have X error and Y error. You can actually have a mean plus or minus the error on every single axis. That's a very, very important tool when you do meta-analysis. Because sometimes you're setting up something and you know Y varies as a function of X, but you can't control X, so you wind up sampling to estimate it, which means it has a mean and error as well. So, believe it or not, that's more common than you would realize. It was actually a big part of my whole dissertation, which hopefully I'll get to in the very last lecture. And what this alone will give you is just each point. So let's run it like that so you can see what it does. What I'll do is I'll just asterisk that out so it doesn't run. And so what that does is it gives you a point and a standard deviation. And notice that the lower bar is almost always larger than the upper bar, except for this little tiny thing. And in fact, when we look at this, look at this. This bar does not overlap with any of those bars. So how the hell did this fail Tukey? It certainly looks different here. Now again, suppose this is a gradient or it's time, right? We had stations and dates, and we're plotting the station means versus dates or something in 289, and we want to connect those. Let's say we want a dot that goes through here, 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 and here. Well, one of the beautiful things about SG plot is you can add as many plots to a graph as you want, which is by just adding more statements. You can add charts. You can overlap a line chart, a scatter chart, and a bar chart. Anything you can imagine, you can do an SG plot. So let's do this. Let's redo this now. We'll take this away, and a line plot is called a series. So a scatter plot is points, and unfortunately, I wish series had this. as an option, because if it did, we wouldn't need two lines. So this will plot the mean and the upper lower, and what this is going to do is it's going to connect it, but it won't put any symbols in because we didn't ask for a symbol. It'll just give you a line. So let's see how that changes. And this program is already sitting, so now we have each of those things with the means connected. Now there's a couple other nasty details here, and that is that notice that this line is blue and these symbols are red. Well, how do we make them all the same friggin' color? We simply add more options. So if we look at the next series, how we customize a graph, I kind of like the blue, so we'll stick with it. I could always add an option here and change the color. So what we're going to do is we're going to change those. Notice we have error bar and then ATTRS. ATTRS stands for attributes. So we're going to tell it color equals blue. And I don't like that. I don't like that open circle. I want a closed dot. So we call symbols. I wish to hell they did. In Gplot, this would be called a symbol. In SGplot, they call it a marker. It's things like that that drive me crazy. So we're going to change the symbol in the marker attribute to a circle filled, and we have lots of options here. We're going to have tons of them. And we're going to change that color to blue as well. So let me go ahead and go to the end here. Yeah, that's the end of it. So let's see how that customization works. And yeah, that's exactly what I want. And by the way, for publications, I could have used black. If you have a series, let's say we had 3 stations. Let's say it's a 2-way design, and these were stations, and this is dates. So you have 3 lines for stations, and I can change both the line type and the color type for everyone. And so now everything is blue, and we've got an upper and lower bound. But what really irritates me about this is I just don't believe the Tukey test. I think that this one is different from those 3. So what do all the multiple comparison tests give you? It gives you all pairwise comparison. But what did I just say I want? I said I want to compare not this with that, or this with that, or that. I want to compare this with the mean of these 3. I want to know, is this one completely different from those 3? Now, is that a common kind of a question? Of course. Imagine a control and 3 treatments. Right? Let's say you're doing an experiment and maybe you have 3 caged treatments and 1 untreated sample you call a control. And when you get done, you don't give a shit about all the pairwise comparisons. You just want to know if your treatments are different from the control. So the question is, how the heck do we compare let's call this our controls just for fun, even though it's not, from these 3? Well, that is called a linear contrast. The linear contrasts are probably one of the most important things I'm going to teach you about the entire semester.
There's no eraser, by the way.
There's no eraser, by the way. So,
napkin right here.
There's a napkin, that'll work. We're not going to take up a lot of room. So let's go. And by the way, I'm going to go through this really quickly. And someone took my clock away too. So I don't know what time it is.
20 after.
But it's actually 11:21 because I can see it down here. So if you look at my lecture notes, I kind of go into a lot of this stuff in horrible gory detail. I'm not going to do that today. I'm just going to tell you the punchlines, and you need to fill in the blanks on your own. Go read the lecture notes. So the bottom line is, what is the null hypothesis here? Right? It's our three treatments equals 0. Right? Our treatments, or all of our treatments, what's our null hypothesis? That all the treatments are exactly the same. So what is a way to, and how do we actually do the statistics? So how do we do the actual statistical test? When we look at something like this, when we look at the ANOVA table, our treatment, our F value and probability for that is 0.05. What is the test? Well, the test is F equals 0, right? 0 meaning there's absolutely no effects. So, what does that mean? That means what this really is y1 plus y2 plus y3 plus y4 equals 0, or this all equals 0. The point is the coefficients of these things all add up to 0. It means there's no effect. So how can we use this trick to test is number 4 completely different from the other 3? Well, it's a piece of cake. It's what we do is we create what's called a linear contrast. So imagine this equals 3, and this equals, excuse me, that's wrong, that's wrong, that's wrong. So imagine this equals 1, and this equals 1, and this equals 1. What does this have to equal to make this sum up to 0? -3. Right? So all we need is a way to take those means and multiply them by these coefficients, and we have the explicit null hypothesis that mu1 equals mu2 equals mu3, but they're not equal to mu4. Okay? The mean of these three are different from that mean. That's our test. And we do that with a contrast statement. So let's show you how to do that. So everything here is in Dropbox on a thing called NAS1 ANOVA with comparison test and back transform, which you probably need for your midterm and your maybe your things. So let's so let's go back here. And now, we don't need to run that again because we already know there's no difference. But let's go ahead and put in contrast statements now. And I'm just going to go ahead and do log n because we know that, because that's the one that's prettier. Because it relates, log n is this picture, right? So we go contrast, and first thing you do is you give this a name, and the name is what's going to show up on your output. So this name is going to be means 1 through 3 versus 4. Does that make sense to you? In other words, I want to know if these 3 are different from that. And so that text string will show up in the in the output underneath the ANOVA table. And now we have to tell it what effect we're going to look at. And the effect here is station. And now we have to give it the coefficients. So we're going to 1, 1, 1, and then finally -3. So it's going to run this on both log n and on x. So let's run that. And now when we go back up, now one of the things that's really important is the order. It doesn't tell you this, but it's going to use the exact same order it uses up in class level information. So you see how it orders station 0-0, 0-10, 0-100, 0-1000? That order is the order in which your means are going to get applied. So sometimes, because of the way characters and numbers get sorted differently, before I do these things, I'll sort them myself. And then sometimes I'll run the ANOVA without the contrast statement, just to check that one box and make sure I've got all my ducks lined up right. And now we have what we had before, but now we have a new line. Right, and here is, this line is not called station, it's a contrast. And notice it looks exactly like an ANOVA table. And now you got DF, you got a sums of squares, you got a mean square, an F value, and a probability value. But now we're testing, hey, are these first 3 completely different from my control? And oh my God, it is. So, what did we just show you? And that was for, that's for log n. It's right there. If we go above, it'll say log n. Let's see if it's also true for diversity. I don't even remember. So here's S. And it's not true for diversity though. So, what did we just learn from all this? Okay? Oh, this does say there's differences now. That's interesting. Well, what I was going to try and show you here was that even because these multiple comparison tests have a tendency to be conservative hypotheses, because you can have, it didn't happen in this case, but you can have a non-significant value for station and yet a contrast statement would show up being significant. Now there's a whole nother extension to this that's really important, and that's with two-way ANOVA. So, this finishes up multiple comparisons and linear contrasts. It also finishes up how to plot some important things. What I need to do now is I'm going to clear out my cache, start with a blank slate, and we will save this program. I'm just curious. So for S, well, for number per core, it's not significant. Let's go down to the bottom. Okay, so for species per core, number of species, this was not significant and that's not significant. Okay. We're done with this. So let me save this for you. We're going to call this let's call this NAS1 linear contrast. So this is actually completely wrong here. So this is using a linear contrast to compare, well, I'll say to test specific null hypotheses. Specific a priori null hypotheses. Okay. So what do I mean by that? What I mean by that is if the design was such that we knew this was our control value and our ultimate goal was to compare our treatments with our controls, this may be an important test. For example, we may want to test each one of these versus one of these individually, but not all multiple pairwise. So how do we do that? Well, if we go 1, 0, 0, minus 1, we're comparing 1 and 4, and we're zeroing out these things. If we go 0, 1, 0, minus 1, we're comparing 2 in my control. And if we go 0, 0, 1, minus 1, we're comparing 3 in our control, ignoring these two things. So this is actually what Tukey is doing, right? With Tukey, what all of the pairwise multiple comparison tests are doing is they're setting all of it's basically doing a linear contrast type approach, but it's setting everything to 0 except for 2 at a time. But that's a post hoc analysis, which is inherently conservative. This is an a priori analysis, which is inherently more powerful. So the point is, figuring out how to come up with these contrast coefficients is the whole trick. And what I typically do is you just count and make sure that the sum equals 0, right? It gets really hard when we have an odd number of things. So let's say we had 5 things, and we wanted to compare 2 means versus 3 means. 2 minus 3 is minus 1. That doesn't add or equal 0. So how do we fix it? Well, it's simple. If we use 6, then we've got plus 2 plus 2, plus 3 plus 3. So let's say you had 5 means. 1, 2, 3, 4, 5. And we wanted to contrast these two with those two. Well, you know, if we go 1, 1, minus 1, minus 1, minus 1, that equals minus 1, right? That won't work. But let's say we multiply everything by 6, okay? What we can do is 3, 3, minus 2, minus 2, minus 2, and then that equals 0. See how that works? So the bottom line is, even when it's hard, it's easy. As long as you kind of think about your fractional proportions. So this is, you know, 2 things, this is 3 things. So if we go 3 times 2 is 6, right? Then it's easy to get 6 divided by 2 is 3 and 3. 6 divided by 3 is 2, 2, 2. This adds up to plus 6. This adds up to minus 6. Okay? And again, if you look at my lecture notes, I give you lots of examples that are common on how to do this stuff. Now, I need to stop that, and I want to go into something called simple main effects. Yeah. So NAS2 composite has dates and stations, right? And replicates, replicate 1, 2, 3, right? And then we have N, which is number per core, NM2, which is extended to number in the square, and S, which is the number of species in each one. But notice that should be 0. So, right, if there's no species, if there's nothing to count, that should be 0. So what happened is, this is when I ran it incorrectly. So I'm just going to cheat right now. I'm going to go edit, put this in edit mode. Did you see how I did that? Go edit, put it in edit mode. Now I can just go here, and I can just put a 0 right on top of that. Let's make sure that doesn't occur below anywhere. There's another one. This is not an elegant way to do it. I'm going to fix that one too. There are a lot of zeros in this data set. Damn, there are a hell of a lot of them. What I gotta do is highlight it and type in your new number. Oops. Okay, so now I can save it. See this little button? See the save button? So now we've got a correct data set. I think I showed you how to fix that programmatically. So recall that if there's nothing in a data set, you have to have a placeholder for that replicate, because you don't want all of a sudden to be 2 replicates, because the mean of 6 when there are 2 replicates is 3, the mean of 6 when there are 3 replicates is 2, right? So you got to get the correct N. And so I have a placeholder in that row for no species. And after I do this, that's got to be deleted. And obviously I didn't do it when I ran this data set. But now it's fixed. So what do we want to do? We want to do proc GLM data equals ed dot NAS, whoops, NAS underscore two-way composite, and classes are, I'll tell you what, we want to do something else first. This says February, May. Well, here, let's do this. Let's say, I'm not sure. Let's say I'm not sure how many gates and stations there are here. And I want to do a little exploration. Is there an easy way to find out, let's say, how many replicates there are or how many things we have? Well, I always like to create what I call block charts. So, right, if we're doing this, if we're diagramming an experiment, right, we're going to do something like this, where we have our stations and our dates. So can we build a quick little chart exactly like that? Okay, it turns out there's a real easy way to do that. That's called proc G chart. So I'm going to go proc G chart. I need to steal this. Copy. And we're going to do a block. And let's do blocks by gate. And we're going to do groups by station. And let's use our summary variable. Now I could do sum bar equals, let's do n, and type equals mean. So if I do this, what it's going to do, whoops, oh, I got to close the data set before I can do that. Okay, close the data set. And let's clear my cache one more time. And I'm going to use a quit statement here, which I use a lot after GLN, and I use a lot after any graphics. Because it turns out these things are interactive, and you can keep adding more statements. It doesn't actually end it completely until you do that. Why didn't that work now? It has more than 12 levels. How about that? Oh, Jesus. All right, let me do this. More than 12 levels. That I wasn't expecting. So, okay, let's do this. Remember, we did this data set called NC, MASP, where we wound up with 75 lines, and there should have been 72. Let's use that one. So this will give me an excuse to show you two things. We're going to explore that and find out where the hell are those extra 3 lines. Now with NC, recall one problem is that, let's pull it up. call it, one problem is in October, we sampled every station on a different day, the 19th to 21st, right? So what we had to do, ed.ncmasp_composite. So what we had to do is create a new variable called period so that each month is separate. And we used the mday function, so month from date. And let's just set them all to the middle of the month, the 15th, and year from date. And let's format period with MONYY 7 dot. Okay? Now let's go and see. Now these are periods. And well, let's run this and show you the effect of creating period. So here's NC. So now we've added this new variable called period so that the 19th, the 20th, the 21st, and 22nd, see the 22nd? They all have the same period now. Well, if we do this, so let's do proc G chart, and now we've got essentially a block diagram where we have our stations A, B, C, D, and our dates. And notice, this is a surprise to me. Notice that it's filling in the empty dates for us too. So it even shows us the months we didn't sample. And that would be the average count. But it's not what I expected. What I was expecting was that there might be an extra month or something with a cell, okay? But that didn't happen. So maybe we better just count the number of replicates. Let's do that instead. So let's go here. We'll go copy, paste. So let's count rep, and instead of taking the mean, let's take the number. Oh no, let's sum it. So this will count the number of replicates each time, right? And if we do that, look at that. We have 6 replicates everywhere except in that cell where we have 12. Okay? So if we go look at April 88 station C, we can probably figure out where. So let's go look at this new data set we've created called NC. And we want to look at April 88. We'll put April 88 at the top. We can see we have a C on April 11th. And we have a C on April the 13th. So it turns out C got counted 2 times. Now, let's say I wanted a balanced design and I wanted to get rid of those extra lines. How do we get rid of those extra lines? Well, first I might ask myself, which one do I want to get rid of? And let's say this is the 12th, the 13th. Oh look, at least we sampled B and C the same day. This is the 14th. So let's go ahead and get rid of the 11th, because at least we have these two on the same day. So what I want to do is get rid of the 11th. Now, one of the things I got to figure out is why this says 6 and not 3. Why does that say 6s and not 3s? I'm going to have to figure that one out. Something is wrong there.
Is that because originally it was sections? 2 sections?
No, there are no sections in that data set. Look, I thought there was, but look, they're not. 1, 2, 3. 1, 2, 3. 1, 2, 3. What's going on here?
Is it because you're summing the actual replicate number?
Oh, it's summing the replicate numbers.
Instead of counting
Yeah,
them.
3 plus. That was dumb. Let's see if we can do this. Type equals, is it n? Will that work? It didn't turn blue, so I get nervous that it won't work. What happened here? No, that didn't work. Oh, frequency it's called. Look. Freak. So one of the nice things, even if you make a mistake, it underlines your mistake and it tells you, look, you could use these kinds of things, but you can't use that. And now we have, whoops, let's go down.
We've got to get rid of the sub-variable term. Quick one.
We got to get rid of that. Yes, now that worked. Okay. Anyway, ways to explore your data set. So now let's go back here and finish what we were starting. So recall we want to get rid of April 86, 88. So how do we do that? Well, we're going to go to data, and I'm going to call it NC just 1 because I'm not very original. And we're going to use our data set called NC. Now I could have also just cut and pasted this whole thing. In fact, let's do that. Copy. Paste. And I'll call it 1. Now, what I want to do is delete 1188. So there's actually 2 ways to do it. I can use an if statement. If date equals, now if I put this in a quote string, 11 April 1988, unquote, I put a D there. You notice how I turned it from pink. Look at this for a second. Look at the effect of the D. See, without the D, it's pink, right? Meaning it's a text string. If I put a D there, SAS knows that that string is a date. It's an easy way to do it. So we could have also used this, right? We could have also used that approach. Then delete. And let's do this again. Copy. We'll make sure we use the right data set. Now, I'm going to turn that off. Let's go to log so we can see what's going on there. I'm going to get rid of everything in my log. Now everything is 3. We have a balanced design. Now let's go see what the log did. Now, it tells you that 75 observations were read and 72 were put out. Okay? There's another way to do this. Go copy, paste. And that is using the where statement. So I'm going to delete that. We can use where date is not equal. Right? We want to keep everything except this. So we could say not equal, right? As opposed to the if statement. The if statement said if it equals, then delete. We can say if not equal. Basically, the where statement is a keep instead of a delete, so it's the opposite. And let's go ahead and use month, day, year this time. And its month is April, the day is 11th, and the year is 1988. Okay, so we'll use month, day, year, just so I can prove to you I can do it either way. And we'll run it again. And now look at what happened. Here, when we use an if statement, it read all 75 observations, then it applied the selection, and you wound up with 72. In the where statement, it only read the 72 observations. Notice you don't see the word 75 anywhere. What does that mean? That means it never even read the row that didn't meet the where test. Now, that means it's a hell of a lot more efficient. It should be more efficient, but it actually took more time. Look at the if statement. The CPU time, the real time was 0.01 seconds. CPU time was 0. It's actually a lot slower to do it that way. On supercomputers, this opposite would be true. If we had a data set with 1 million lines, being able to skip the things you don't want would actually might save you some time. So the computer geeks are always telling you should use where over if, but I don't think that's necessarily true. There's something more important. Every place where you can use the word data, you can use where. So let's do it this way. So let's go back to G chart. We'll copy that. Let's put the where right over here. Now the first time, it's going to print what? It's going to give us the 75, right? Well, we can apply the where over here. Like this. You put it in quotes. Where, and we can just copy all that. So we could put, x equals y. We can put any kind of test here. And let's see what effect this is going to have. So again, the first time we did this, proc G chart, No, I deleted that already. But you remember this is 75. Whoops, let's go down to the bottom. Whoops, it didn't work. Oh, I forgot the equal thing. Oh, you can't have a not in there.
Do NE.
That's what I'm going to do. Let's see if that works. Nope. Oh, I'm missing the equal sign. I think you need equals right there. Yep, you need an equal right there. Let's try one more time. Damn, still didn't work. Enclosed in parentheses, okay. Enclosed in triple parentheses now. Let's try that. Yes! Now, so let's compare this with this. So here's the punchline. Every time you have the word data in any proc, just about all the programming language is actually available as an option. I gotta move that. You just have to add a lot of parentheses, a lot of equal signs. So the any is identical to this, all right? And actually, I'll bet this would work now that I've got the parentheses.
You could move the where underneath the block. You could move that out. It doesn't have to be by the data equals.
Oh, I could have put it,
Yeah.
I could have put this line here.
You could put it underneath where it says block period, and then you don't need all that junk.
No, I don't think you can. And I don't want to mess with it. You can mess with it later. But my point is that these tests, I'm pretty sure it would work there too. The other thing we can do here is we can keep and drop variables in a proc. But this whole approach works with every single proc. It would work with proc GLM. It would work with any other plot. But normally what we would do, you'd have to be super lazy if you felt like this was too much work to use this approach. I almost never do this. The only time I actually do this a little bit is when I'm using proc means and I don't want the type and the freq variables. You can go drop equals type and frequency, and then you'll just get a data set of just the mean values for each row, okay? But anyway, this ties up two other things I wanted to show you, which is showing you a little bit more about data exploration, and finally, showing you how to subset data sets using the where and the if statement, okay? That's something that you may need for your projects. You don't need any of the things I'm showing you right now for the midterm, but I wanted to get to it. Okay, so let's save all this. what should we call this? So this is NASP explore and subset. Okay? I always give it a name first, .SAS, and I put it in the first row. So now I'll save it. What did I say I was going to call it? See, that's why I do it, because I can never remember. NCMASP, explore and subset, .SAS. Okay, so that program's saved and you have that now. Oops, I'm running it all again. Not what I wanted to do. What I was trying to do is hit my X button. Now, let's clear the cache. I want to show you one more thing before we run out of time. And that is how to use the linear contrast. And this will finish up the two-way stuff. So if we go back to NAS2, well, I'll tell you what, let's use this one. Okay, so now we have a balanced design. Right? And let's go ahead and look at it and see. We actually already have log calculated. So we've got dates and stations. We've got 72 rows. So let's do our proc GLM. Let's do a 2A ANOVA, right? So we have two classes, period and station. And our model is going to be number per meter square, log number per meter square, and S equals period ST, and that's all set, right? No. What about the interaction term? Period star STA. Now let's say I am too lazy to write all that out. You can actually create full block designs with the pipe. So if I put a pipe in here, what that means, build me a model with all the interactions. When we do three-way designs and other complicated designs, this is really useful. Because sometimes it's hard to remember all the details. But for right now, let's just use that. And let's do means. We'll do it for station, tricky lines. Let's do means for period, tricky lines, and run. So let's do this. Now, so here's our period. We've got 6 periods, 4 stations, 3 replicates, 6 times 4 is 24, 24 times 3 is 72. Everything adds up, right? And now when we look at our interactions, you can see for the first variable, number per meter squared, we have differences. We have no differences with periods, but we've got differences with station, and the interaction plot's not significant. There's your interaction, but that's not significant. For lot number per meter squared, it is significant. For richness, it is significant. So let's just work with the richness variable. So when we look at the richness variable, how do we find if there are, and if I look at this, I think this is A. I might say, you know, I still think that A is completely different from B, C, and D. But what does the interaction term tell us? It tells you that the test for station is nullified because you have significant interactions. So what do we do with significant interactions? What we do is we create only 2 minutes left, a simple main effects test, then we run a linear contrast, and we get our answer that way. So we're going to do it just for S, okay? Because we know that the station is no good because the interaction term is significant. So the first thing we got to do is create a one-way design. So we go data, we'll call this NC1, set NC. And what we got to do is create a new variable we'll call treatment. And what we're going to do is we're going to take let me look at this real quick. So this is over 2 years. That's going to be a pain in the ass, isn't it? No, let's just do it anyway. So let's take let's compress. Compress means take all the blank spaces out. And we're going to add the word station first. STA. We're going to add it. We're going to add the text string. So we use a double pipe. And we're going to add a dash. And we're going to add that to period. Then we'll go run. So let's look at the effect of this. So now we have one treatment. So we'll look at NC1. Oh, look at that. It changed them to numbers. That's ugly. I was expecting to see C and October 1987. But the program, this was a number, so it gave just a number. So what we've done is we've got the word station, and then we've got dash, and then we've got the period, which in this case are numbers. Now, I don't like that, so why don't we I'm out of time, so I don't have time to really get fancy. I'll get fancy later. But what I'm going to do now is flock sort data equals NC1 by treatment run. Let's close that up. And now I've got my A's, 149s, 2010s. It's very difficult to see. But my point is I can now do a proc GLM and I have one class, right, TRT, and my model is going to be S equals TRT, run. And this is a good example of a lot of times I run these first because I don't know what's going to happen here. And you can even see here, all of these A's look really different from these other ones. So now what I can do is I can take this and I can cut and paste it. Copy. Well, hell, I don't even need to. Look at this. We've got 24 of those, right? 1, 2, 3, 4, 5, 6 are A's. And they're all showing up in the right order. So I've got 24. We've got 6 of these. So how many are the rest? What's 6 times minus 24? 18? So that means these are going to be minus 3, minus 3, minus 3 6 times. And this is going to be all ones. Okay? So now, we're going to copy it, we're going to run it again. Now we're going to create a contrast. And this is going to be A versus B, C, D. Okay? And it's going to be treatment. And we're going to have minus 3 space. Copy. 1, 2, 3, 4, 5, 6. Then 1, 2, 3, 4, 5, 6. And I'm going to copy that 3 times. Copy. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 18. So this contrast says all the A's are different from everything else. And it's not there, which means I have an error.
And you have 1 extra negative for each. Yeah, 7.
Got 7, huh? Try one more time, feeling. And there it is. And the answer is yes. A is different from B, C, and D. Even though doing it 2A, we couldn't find it. Go. I'm sorry I went over so long. I'll put this on the web.